Thank you so much. I'm reminded of the old quip, everybody complains about the weather and nobody does anything about it. Well, in this presentation we want to talk about how we respond to some of that inherent variability in the renewable energy sources. I think Alan and Pramod have really set up this presentation well because we heard about something about the power electronics themselves and how they can provide the basic infrastructure for solving these problems. We heard about what some of the variability problems are. And so now what I want to do is talk about how we actually will move onwards to account for the variability in renewable energy sources and adjust the way we behave as consumers in order to best use the energy that's available to us. So in thinking through what we wanted to talk about in this presentation, Alan and I have been working in this Grid-Connected Power Electronics Center for a number of years now, and we decided this was not the audience to talk to about detailed power semiconductor devices. But in terms of how do we integrate the various forms of renewable energy sources into a system, the variability of renewable sources and the need to make even things like renewable fuels available on varying time scales is kind of an important thing here. And so what I'm really going to focus on today is an energy management system that is primarily at a residential level. Now I'll talk a little bit about an industrial or commercial extension of that, but the idea here is that we want to integrate renewable energy sources into the home infrastructure, controlling the flow of power between various sources such as photovoltaic or wind energy systems, energy storage mechanisms such as batteries, and smart loads which are turned on and off at the right times of the day to make best use of that energy as it's available. The things that partly facilitate this are the dynamic pricing that may be available in the electric power infrastructure. Most of us these days pay a fixed rate for our electric power. We pay 12, 13, 14, 15 cents a kilowatt hour for power. But time of day pricing or real-time pricing are emerging trends, and this makes the time variability of the cost of energy an interesting factor in deciding when to use it. Also, there can be incentives for actually curtailing the use of your power at certain times of the day. And so our focus in this system was to look forward to a future energy state where pricing information is known and communicated. A lot of other information is available, for example, weather information and the behavior of the home's occupants, so we can make these smart decisions. We also wanted to consider the fact that maybe homes will be configured a little bit differently in the future. I guess everybody's noticed that now you can get those little electric outlets that have the little 5-volt ports in them to plug in your USB things. Well, we think there will be a greater trend towards DC power in the home, and so we've configured this system so that it supports that kind of thing. So let's talk a little bit about what is the opportunity here that we're trying to exploit. First of all, we see that there will be widespread adoption of photovoltaics. Even though you heard it's about 1% of 13%, it's a pretty small number. And yet right now, the dollar cost of power from photoelectrics is getting very similar to the price that you pay as a consumer. It's a long ways from what the price of power that you produce as a producer of power. If you can produce power at 2 cents a kilowatt, 2.5, 3 cents a kilowatt hour from coal, it's hard to compete with that. But if you happen to be paying something closer to 20 cents a kilowatt hour for your power, it's much easier to compete. So we see that people will be starting to adopt photovoltaics much more quickly at the home user site. Other kinds of renewable power sources are becoming more viable. Yeah, maybe we'll have fuel cells in our homes one of these days. Maybe they'll provide hot water and other home heating applications. We know that power pricing is volatile, minute by minute, hour by hour, day by day. You heard about different pricing strategies. You would be amazed at the number of power markets there are. And if my home was smart enough to participate in those markets, I would be able to perhaps make some money on that. This real-time or time-of-use pricing, those are actually different, slightly different concepts in subtle ways, encourages more responsible power behavior. This is why there's a lot of interest in smart meters on homes, because if you know what your consumption is, you can do something about it. I put in here that I want this to encourage us to be more Danish. You recall on Sunday, the representative from the Danish embassy was talking about how the Danes will put up with a lot of stuff, but they're very responsible people. Well, we want to become more Danish in our use of power here. Then I also recognize that energy storage is coming. While you heard a minute ago that energy storage is not viable at a competitive price in the electric grid right now, again, part of the problem is we're trying to compete with a few cents a kilowatt hour at the grid scale. But at the consumer end-use site, the price differential will be larger and the price is much higher. That may make it competitive much sooner. And then there are emerging markets in power aggregation. So there are many new business opportunities. My home might be smart enough to talk to my next door neighbor's home, the other homes around the neighborhood, and they all talk to somebody who aggregates small amounts of power fluctuations from all of our homes into a market that says, I'm going to sell you megawatts of power for the next hour. And then, of course, all this stuff is connected through this ubiquitous internet, and that's the thing that really enables the coordination. So our research environment we're coming from the electrical engineering perspective. Our research group has worked on things like hybrid power sources, on ship power systems. A lot of our funding has come from the Navy. Well, that's a perfect example of a microgrid. We were doing some of the microgrid research before the microgrid was popular in the public environment. These systems are very multidisciplinary. Power electronics, control systems, thermal systems, the energy storage, controls, electrochemical. You have to involve a wide range of researchers in order to really tackle these systems. We also realize that we're going a little bit back to the future. If you go all the way back to the beginnings of the electric power system, Edison's plan was, I'm going to put a little DC power source in everybody's backyard. Maybe everybody at the time almost had to have their own engine mechanic to keep the thing running, and his business model was, I'll sell the little power plants to everybody, everybody will have their own. And the reason was you couldn't transmit power very far because at low voltages, the losses in the wires were tremendous. Then somebody named Tesla came along and had this bright idea for a way of stepping up voltages, and alternating current was and transformers enabled us to raise the voltage so that we could transmit power very long distances, and that became the source of the central generation station with radial distribution out to all of the loads. 100 years later, that's pretty much still the same way that we are working. And yet now we're starting to incorporate photovoltaic sources. Those are inherently DC. Fuel cells, those are inherently DC. Batteries, those are inherently DC. And the remarkable thing is that everything in your home, practically everything, really wants DC power. You just give it AC because that's what you got. So we're looking for how do we make more efficient use of the power, and part of it is in preserving the DC characteristics of the power in the distribution network. Now, I mentioned that this is a very strongly interdisciplinary problem. If I look at the way power is used in the home, a remarkably large part of it is thermal. The part that is computers and electronics is currently shrinking. I can remember a day when I had a desktop computer, my wife had a desktop computer, they ran 24 hours a day, we never shut them down, they had CRT displays, 200 watts, 300 watts, continuously, day in, day out. Now what do I have? I have an iPad that charges in an hour or two at a few, an amp of current. The power demand is minuscule compared to what it used to be. The same is true in lighting. The original use of the electric power system was for lighting, not air conditioning and all that. It hadn't yet been invented. But lighting demand was fairly large not so many years ago. It's shrinking as we go to compact fluorescence and LED lighting. So the parts on the left side of that picture there are getting smaller and smaller. In fact, the parts on the right side, the space heating, the water heating, and all those things, they're getting smaller too. And more interestingly, as we go to higher energy efficiency, better insulation in home systems, we're getting longer time constants. Longer time constants are really, really good. That means I can put thermal energy into or out of a system at one time, and then it kind of hangs around for a long time. So I can shift the use of my power in time more and more efficiently. So our opportunities to reduce cost in this system are several. We can reduce demand. You do that by increasing insulation value in the home and that kind of thing. You can reduce demand during special pricing intervals. So if you use time of use power pricing or real-time pricing, you may avoid using power when it's expensive and use it instead when it's cheap. You could respond to utility requests for curtailment. That is, stop using your power or reduce it by a kilowatt or 10 kilowatts. You can time shift your consumption. That is, move loads temporarily from peak price time to times off-peak price. Pre-cool your house, pre-warm your water. You know, one of the interesting things about water heaters is everybody wakes up in the morning, takes a shower, and that's one of the worst times in the winter for power prices. And you heat all that water up and then you get away and leave the house. So that hot water sits around leaking heat out of the system all day long. If we were a little bit smarter about that, we would have heated the water before we needed the hot water and leave the tank empty and cold for the rest of the day. We'd be using our power a lot more efficiently and at better times of the day, and we could maybe do it when renewable energy was available from a wind system or something. And then when I have renewable power like solar, it's only available when the sun is up or when the wind is blowing, so I need to either use it then or store it and then use it later when I need it. If the utility has time of use pricing, I may be able to sell it back at a competitive price. So why does time affect cost? Well, here's a graph that I just pulled off of the PJM website about 2 days ago. This shows a typical winter day power demand cycle. The fluctuation that you see between the minimum and the peak is about 25% of the base load. So the bottom end of that graph is at about 80 megawatts, the top end 80 gigawatts, and the top end is about 100. You notice there's 2 cycles per day. That's 1 day, that's not 2 days. There's an early morning kind of demand when everybody gets up, goes to work, warm up the house and that kind of thing. Then nobody's around during the afternoons. The sun comes out, the day warms up a little bit, power demand goes down, and then in the evening it goes back up again. So a typical pricing strategy for a time of use power pricing is a 3-tier kind of schedule that's very low at nighttime when the power demand is very low. It comes up to a higher value in the morning, drops to a middle value during the day, back up to a higher value in the evening, and back down to a low value at night. That middle value is often called the shoulder price, and you wonder why in the world is it called the shoulder, because it doesn't look like a shoulder there, but on a summer day, the head is in the middle, the high price, and there's a shoulder on each side, and it kind of looks like the profile of a person. So time affects cost because of the demand structure, and if we're trying to flatten out power demand so we can run all of our resources either in a constant generating mode without ramping them up and down, then we'd like to incentivize the shifting of power demand from away from the demand peaks and into the demand valleys. Now, power plants generally like to run at constant power output, nuclear plants especially, but all power plants are a little happier when they're running in steady state. wind energy systems are going to run when the wind is going to run, and solar is going to produce power when the sun is going to be out. And so our traditional tendency to try to flatten power consumption may be disrupted in the future, because instead of trying to push the peak consumption profiles down to get everything flat, we may be trying to push them to the optimum use times based on when power is produced. Here in the Southeast, this is an SEC meeting after all, the winter and summer prices are a little bit different than they are up in the north. Here you see there's still only a daily winter price, but it moves earlier in the day. So power on the South Carolina Electric and Gas, if you elect to use a time of use pricing, is about a little less than 10 cents a kilowatt hour during much of the day, but during peak times in the winter it goes up to about 26 cents a kilowatt hour, and during the summer a little higher, around 28 or 29. I guess we're trying to reduce the use of air conditioning because it's probably not such a critical health issue, but we don't want to penalize people for trying to stay warm in the winter. Maybe that's the difference. Or maybe it's just the price is a little bit less, demand is a little bit lower in the winter than it is in the summer. So the schedule varies by season. Similar kinds of schedules apply to when I feed power into the grid. And I apologize, some of the text here is probably a little bit small. I had to copy this out of a student thesis, and it was a picture, not something I could edit. But the pricing can follow time of use schedules, and you can get more value for your photovoltaic power during an on-peak pricing interval. But a lot of electric utilities want to reimburse you for electric power that you supply back to them at what's called avoided cost. What is avoided cost? It's the cost they didn't have to spend to produce it with whatever their cheapest resource was. What is that? 3 cents a kilowatt hour. I can never make a photovoltaic system pay for itself at 3 cents a kilowatt hour, at least not right now. So I really would like to be able to capture that energy and use it at a time when it's most valuable to me. So that gets to the heart of this local energy management system, where I'm showing here on the left side this thing that we're calling a smart green power node. It's a smart power router that allows us to manage the flow of power within a home, and kind of importantly, keep that energy within the home, within that little island that I've shown there, because if the grid goes down, this home will continue to have power even when others will not. Whereas if I use the conventional photovoltaic feed-in strategy called net metering, there's actually one meter that power goes out to the grid from the PV, and another one where power comes back into your house. And you pay for the difference in the amount of readings on those two meters. Well, if the grid goes down, my photovoltaic has to trip offline. It can't energize dead power systems. So my photovoltaic plant doesn't make power, and I can't use it even inside my home. So this local use of energy management allows me to keep my home alive even in the face of disasters like Hurricane Sandy or great snowstorms of the Northeast. Now, it turns out every home is quite different. So this smart system has to be smart enough to account for the variability or the individual habits of the homes. Here I'm just showing 6 different homes with 6 that were individually instrumented by American Electric Power a few years back. And you can see the time characteristics of power demand through a 2-day interval is highly variable. One day, the first day doesn't look a whole lot like the second day, and no two houses tend to look a lot alike. So my system must be pretty intelligent if I'm going to anticipate when power is going to be used and what the price of power will be and when it's the optimal time to, say, charge a battery or to turn on the water heater. There's other reasons why storage is very useful. If I look at the peak production time of photovoltaic power, in the winter, it does not match very well the peak demand time. So on that top graph there, I'm showing how that there is misalignment there during the winter. The solar power graph is the kind of the bottom line in the top half of that figure. And the average home demand is the red line there up near the top. And the power pricing schedule, time of use pricing, is that trapezoidal kind of shape in there. So my highest value for photovoltaic power is mismatched to when I'm actually going to make it. At least it's better during the summer. The afternoon peak power demand is for cooling in the summer times, and that is generally when I have photovoltaic power available. So I might not need to do much time shifting of my power use in the summer, but I almost certainly will need to in the wintertime. So in building this system, there's a whole lot of power conversion circuitry, and I had to put this picture in here because in all the presentations we've seen very little of the power circuitry, the power electronics that manages the flow of power. We've told you that power electronics is the key to doing this, but what's inside there is transistor switches that are turning on and off literally tens of thousands of times per second. You don't want to just kind of crack the valve a little bit. That's very, very, very wasteful energetically. So these things are turning on and off tens of thousands of times per second, maybe even hundreds of thousands of times per second to manage the power flow, each switch individually controlled. Well, that takes, again, control over very many time scales. All the way down at the hardware level, you're turning all those switches on and off individually with more or less nanosecond precision. As you come up in the hierarchy of the control system, and now we're not even talking about controls for the whole world out here, you know, the whole Eastern Interconnected Electric Grid. We're talking about one little thing inside our house. There's still many levels of control there. And I want to focus a little bit on the system control because this is where some of the most interesting stuff happens here with respect to energy management. So here's a variety of the control inputs that we need to worry about. What is the weather? I don't know, how many of you pay attention to the weather? I'm a sailor. I pay attention to the weather all the time. I've been energy harvesting for 30 or 40 years, I guess. But this new website that has wind flow streams, I think it's hint.fm or something like that. You have to look that up. That's pretty cool. It's got one of the nicest visualizations of wind flow streams that I've seen. So much information is available about the weather now that there's almost no excuse to not know what's generally going to happen in your area. And so if I take into consideration the wind, the temperature, cloud cover, I can predict my heating and cooling demands. From cloud cover, I can also predict things like anticipated photovoltaic production. I can measure the temperature of the water in my water heater. I can anticipate what my use cycles have been. I can measure the state of charge of a battery in my system. I can look at power pricing, which has a very dynamic characteristic. I can consider the home comfort preferences that I have and what is the current temperature of the home. And I can do statistical analyses of the homeowner behavior in terms of turning on and off the things that we're going to turn on and off every day, and we want the power right now. We can't plan for it in advance. When you look at all those inputs, you can make some very high-level control decisions that amount to more or less two things: setting set points for thermostats, air temperature, water temperature, and setting the battery charge or discharge rate. If you control those two things, you control almost everything you need to control in the energy flow system. I'm going to skip that slide there and show you now. So here is an example of how we are able to reduce the demand for power during the on-peak power pricing schedule in this home energy management system. And there's a lot of lines on that graph, but the key thing is that by using a combination of photovoltaic power, which is inherently somewhat unpredictable, and a battery energy storage, I'm able to, and in scheduling when appliances come on, I'm able to dramatically reduce some of my consumption during the periods of high peak power, and I'm able to recharge batteries at off-peak times and make maximal economic advantage from this energy management system. In doing this study, one of the things we discovered was even just a battery saves money. You don't even have to have the photovoltaic system there, but a battery is able to time shift power quite efficiently, and these results are terribly sensitive to things like the pricing strategy for on-peak and off-peak and so forth. But even a battery allows me to save a significant amount of power. I'm going to skip that one as well. Then I mentioned something about the short and long-term pricing in the energy grid. This is again a snapshot off the PJM website that shows the various prices, and you'll see in some markets at some times prices are actually negative. Okay? They will pay you to take power sometimes. If you're able to capitalize on this very dynamic pricing structure, you're able to then really minimize the cost of your own energy. We can extend this same kind of process to commercial customers, and we did this with some agent-based strategies for communications between different buildings and energy management systems. Going to skip through all of this and show, well, in a nursing home situation, we were able to affect a much better price for that nursing home by avoiding consumption of power during on-peak periods. So what are the presentation takeaways here? Well, first of all, energy storage and photovoltaic sources coordinated through power electronics with intelligent controls can provide some significant cost benefits to both residential and commercial power customers. If I use smart scheduling and coordination of these resources, they can have significant financial benefits, and they can increase the uptake of renewable energy resources. Many of the renewable energy resources are highly variable and non-dispatchable. That means I can't call on them when I need to. And the loads may be only semi-predictable and only partially manageable. So therefore, load buffers are essential. Batteries are a big part of that solution, but also fast ramping power sources can be. And so in the context of this group, when we're talking about renewable energy systems, I think the one thing I want you all to remember is if you produce a renewable energy resource that is able to adjust dynamically to demands on its power, it will have much more value in the future world. And we can't all try to be like nuclear plants, run flat out 24 hours a day. Thank you.
Well, thanks, Roger. I believe we have time for maybe one question from there. We have someone? There's a question right here.
Hi, thank you. That was a great talk. I was interested in sort of the battery technologies that would be implemented on a home-by-home basis as opposed to the very large battery operations that would be for a commercial application.
So in our prototype system, we're just using a lead-acid battery, pretty low technology, roughly 10 kilowatt hours in size. And again, the optimum size, we did a lot of economic studies on this, and the optimum size depends on the size of your house and your energy consumption habits and a lot of other things. But interestingly enough, that size is very similar to the size of the battery in an electric vehicle. And so if you imagine that in a few years, many people will have electric vehicles in their homes, you may be able to use the electric vehicle as a significant part of your energy storage mechanism. It's almost identical in size to what you would need in the home system.